Nice and bright, or is it the afternoon with paella? Do you ever feel that your application's like it's just eating a lot of paella? And do you blame it on the runtime? Is it your VM? Is it your JVM? Is it V8? Or is it something else that maybe is slowing down your application? What I want to explore here today is, are native languages faster, or are managed runtimes reasonably fast? Can they keep up? It's a kind of really interesting thing to look at. So I spend some of my time in finance these days, still do, spent a lot of time there, where I'll be dealing with teams who are arguing all the time about which is faster. Is it C? Is it Java? Is it C#? Is it something else, C++? And there's usually some really interesting wars that are out there. And people know I program in more than one language, so they'll ask me this question quite typically. It's kind of, really, what is my preferred language for writing sort of high-frequency trading applications on? And if I'm honest, and I actually said to them, if I have to do something, I have to do it quite quickly and make it perform, Java is usually my answer. And I usually get this bit of reaction. It's like, oh, really? Java? And it's usually followed up by this question. And it's like, would you really want to build sort of, that needs to be something that's low latency, high performance, but on something that's GC'd? Because when you got garbage collection, we end up with nasty pauses. And the sort of, people think this is crazy. You wouldn't do this in finance. And usually the C++ people in the room have got this sort of attitude at this point. They just think it's sort of like, I'm just so stupid to even suggest this sort of thing. So let's have a bit of a look at sort of what we're going to cover here. So I want to set some context to give you some background on what we're going to cover. I'm going to talk a bit about runtime optimizations and what can be done in runtime in our modern VMs. I'm going to cover the elephant in the room, which is garbage collection. It's always brought up as a major issue. Like, where are we today with garbage collection? Where is it going? I'm going to follow that. And then I'm going to focus on algorithms and design and where that sort of fits into everything that we end up doing. So let's start off. Let's set some context here to begin with. And to be very clear up front, a managed runtime is not always a good solution to a problem. There are some cases where it just doesn't fit. Like, here's a really simple one. If I want to do latency arbitrage, and this is where I need to be the absolutely fastest person in a market trading some financial instrument to win, because you're going to be trading on time, seeing something happen, and reacting before everyone else. Well, if you're actually doing that, you're not programming in a high-level language, typically. You're not even writing assembler these days. You would not be writing C or assembler or anything to that. What you'll typically be doing is programming hardware directly. It won't even be running on a server. It will be running as an FPGA or an ASIC inside a switch very near the financial exchange. So it's a very different sort of world. And people often sort of, they get a bit lost. What do we mean by fast? So the real question here is, like, are the native languages faster? Can we write code in native languages that runs faster than code that runs in, say, JVM, the .NET runtime, something like V8? Can it actually be faster? And it can be quite surprising in some cases. Because the fundamental thing we have to do is follow the evidence and not opinion. I sort of bang on a lot about science and how we don't do science. Well, I'm a computer science major by background. And I think any subject that puts science at the end of it isn't a true science. Like, physicists don't put physics science. You don't get chemistry science. It's kind of the ones that are sort of growing up and working this out. We kind of like add science on, pretending we actually do it. Because real scientists follow the evidence, they measure, they follow up on things. So if we were to really measure and look at, can we make a native application faster than a managed runtime application? And in truth, with the right evidence, it shows you if you have got infinite time, infinite resources, and infinite skills within your team, you typically can make a native application faster. But we don't all have infinite time. We don't all have the best people we can get. We don't always have all of the hardware exactly that we want. So what's the right compromise in this, and where are we kind of going with this? So let's start off and look at some of our performance issues and where our performance really starts to matter when we're running our applications. And I want to focus on running on CPU. I'm not talking about distributed systems here. I'm talking about networking calls. Just if we're going to compare languages, we're really looking at our performance on CPU. So how much time does it take to add two integers? So if we Load integers into registers, we do an addition operation. How much time does that take on a modern CPU? Anyone know? 1 micro, heard? 1 cycle. It's actually correct. Yes, it's 1 cycle. Register to register addition is only 1 cycle for integers on a modern CPU. And if we're running at sort of 2 or 3 gigahertz, that's well less than a nanosecond. It's a very, very small amount of time. Kind of interesting. But let's go with something more sort of substantial than that. Let's say I've got a gigabyte array, and I want to go through and I want to sum up all of the values in that array. Now, that isn't just adding 2 registers together. We have to load in from memory into the registers. We've got to sum things up, so we're doing an addition. We're also got a loop that we're counting over and over again. How long do we think it's going to take per operation, so per number of elements in the thing? So if I've got a 1 gigabyte array, if it's got integers or longs, then it doesn't really matter. But per each step in the process, how long will it take? Any ideas? Order of magnitude longer? 2? Kind of interesting. Let's write a benchmark and find out. So we'll write a JMH benchmark. We'll go ahead and sum up all of the elements in an array, and we'll take the average time. So we'll divide it by the total number of elements in there, and then we'll get the cost per individual operation. What answer do we get back? Well, it's less than 1 nanosecond, 0.8 of a nanosecond per operation. Does that make sense? Have I got a silly benchmark going on here? Kind of interesting. Well, yes, it takes 1 cycle to do the addition. We have to also be incrementing a loop counter. We've got to load in the value. We've got to store back a result again. But you'd be surprised what a modern CPU can do. The sort of view of the sort of von Neumann architecture and a single ALU is not what we have in our modern servers. This is a Haswell CPU. Inside a single core, I'm talking about across the socket, within a single core, we have 8 execution units. We can be doing multiple instructions at the same time. So the addition of the loop, the value that we're summing up, the loading of the next value, the storing of the previous value, they can all be happening concurrently. We get a lot of parallelism and a lot of concurrency even on a single thread in our hardware. So we can actually be doing this at less than a nanosecond per operation. That's if we're going through an array, adding things up sequentially. But let's make it a bit different. What if the access pattern is different than just going through it sequentially? So we're not just going to stream through sequentially. We're going to go in all sorts of different patterns, like let's go random within a page, random across the whole array. We'll do the same number of operations, but we're going to mix it up a little bit with different access patterns and run these different tests. Well, we end up with this set of results if we do that. We're sequentially going through the array, less than a nanosecond. Let's go in random within an operating system page, add up all the values, then go on to the next operating system page, then on to the next operating system page. It's 2.7. It's gone up a bit. Let's do it where we'll go random within the page, but the last value we had must feed into the next step of the calculation. So we've got a dependency on the steps, so the steps can't happen in parallel. Or how about let's go random across the whole heap, or random across the whole heap where we're feeding in the value of the last thing that we've done. And we notice that the times are going up quite a lot. So random across the whole array with the last value being fed in is up to nearly 90 nanoseconds. It's doing the same amount of work, but the pattern of access makes a very large difference to that. So while we got particularly the difference between this dependency-based one and the random, well, one of the things our CPUs can do is they can go fetch memory without blocking. Our CPUs are non-blocking. What they'll do is they say, I need an address, I got to go get it. I can go get it, but whilst that's happening, I can go process another instruction. We can have 10 in-flight cache misses per core happening at the same time. So that's why the random without the dependency is much lower, because it continues to make progress. We get so much throughput on our CPUs. Our hardware friends have done amazing things for us. But this is a really interesting problem, this data-dependent loads. So if you do something and that value has to feed into the next step that you're doing, you cannot continue to make progress. It doesn't matter if your CPU can do things concurrently or in parallel. If the next step is dependent on the previous step, we're stuck. And this starts to get us. So we talk about this as pointer chasing. And so our choice of data structures, our algorithms, a lot of this comes back to basic mathematics. If the problems we're dealing with are commutative, associative, we can do a lot more in parallel. So kind of good old math is going to come back again. Our CPUs are not going to get much faster. We're going to have to get better at our algorithms. And that's fundamentally going to go back to mathematics. Not really complex mathematics, but some basic mathematics that we need to start thinking about. So that's doing operations on memory. Notice we're 2 orders of magnitude difference between how we hit memory versus executing an instruction. What you see if you profile at a low level these days is the instructions you execute are almost irrelevant. They're free for most applications. Unless you're doing sort of more extreme number crunching and you really are pushing that side to the limit, which very few business applications do, it's all about the memory access. And the memory access things is all down to data structures, layout, other things that it's not necessarily about language. It's not the language that changes that. And let's explore what some of this means and what our runtimes can do for us. So, kind of quick recap. Memory is transported in cache lines now. So we move around units of memory. There's 64 bytes at a time. So things that are together end up all being moved together. So if you have an object, fields are likely to be next to each other. They're likely to be in the same cache line. So if you access one field, accessing the other field that's next to it is effectively free. If you're going across to another object, you have a cost. It's now a traversal of the link. So good modeling starts to really matter here. The memory is also managed in operating system pages. And this is where there's a difference between going around the page versus going across the whole heap, because we've got other little caches that convert our virtual to physical addresses and things. So locality of reference happens on the cache line. It also happens on the page level. So keep things together, we get much better performance. But also, our memory is smart. If it spots patterns of access, it can prefetch the memory before we even need it. So if we kind of bear some of this in mind, like temporally, using data close in time, spatially, using it close together, and also thinking about what's our patterns of access, we can get much better performance. So can our languages or our runtimes help with some of this? So let's explore that. So let's look at runtime optimization. One of the interesting things that our runtimes can do compared to our static compilers is they can, at runtime, take real data from an application and make optimization decisions based upon that. And that's a really nice thing. Now, we can do this with some of our static compilers. So some of our compilers will allow us to do a build that will gather profiling information. You take the profiling information back and you recompile again. Very few people actually do that. And also, it's stuck now that those tests that you've done better be representative of what the real application is going to do. Whereas a managed runtime can look at your code, decide what it's going to do, make some optimization choices. But it can also take these bets and revoke them if it's wrong. So it's okay to make mistakes. That's the nice thing is we all accept that we make mistakes, we recognize them, we fix them, we can go back. Making decisions ahead, like statically making ideas in advance, we can't go back and fix them. So static compilers don't really fit with an agile mindset, especially when we want to work when we don't know what the data is going to be. So let's look at some examples. So I've got a little block of code here. I've got a method foo. It's got some code at the top. It's got a condition with an if block in the middle. It's got some code in there, and it's got some code at the bottom. We need to compile this up. We need to turn it into some assembly and machine code to run it. So we've got a block at the top that includes the condition. We have a block inside the if statement itself, and we've got a block at the end. And so we're going to come into this method. If we can run down sequentially through the whole thing, it works really nicely with our memory subsystem because code is still just going to exist in memory the same as our data exists in memory. Now, in a static language, I can hint and say, this branch will pretty much always be taken, or it'll probably be seldomly taken, but that requires upfront knowledge. And when you've got a very large code base, this is really hard to do. There's loads of war stories from the Linux kernel where there was lots of hints in, and then things over time changed, and they don't work anymore, and they all had to be moved back out again. So there's a lot to be learned from, can we do this? But at runtime, we can actually measure based upon real data, make real decisions, and optimize. So what the compiler might decide to do is, you hardly ever go into that if condition. I'm going to compile up block A and block C and put them right next to each other. And I'll put a trap in that if you ever do go into it, I can jump off to that code and do it. So it's a special case. I mightn't even bother compiling it. It could just go into the interpreter at a later stage. So it's really simple things that it can do. And if it discovers it's wrong later, it can back that out and re-optimize it in a different way. Choices it's got based upon real data. Branches can even be more subtle than you think. Ternary expressions. Is I greater than 7? Say it pretty much always is. We can rely on the branch predictor inside the CPU will give us good performance. Our branch predictors are actually very good. But if the branch is unpredictable, if 50% of the time we don't know whether we're going to take it or not, the branch predictor doesn't help. It has to go back again. We've got nice instructions in x86, like the cmove instruction, that will let you do this without a branch, and it becomes more efficient if your probabilities are close to 50-50. If your probabilities are close to 595, it's not worthwhile. At runtime, we can measure the code and decide which instruction we actually generate. So we can choose which CPU instructions actually get spit out. Makes quite a difference to the performance. Methods that have got other methods inside, choosing to inline. So again, with a static compiler, we can choose in advance to inline code, but are we right? Do we know we're inlining the right code? If we measure, we can choose what we inline. And so we could be executing the top block of code. We run down through foo, we hit bar, we have to jump out to bar, execute the code in bar, and take the function call overhead of that, then return back again, and then go forward and do the next block. It's typically what you would have to do. But if we decide that this code is very often called, and it's a very hot method, how about just run block A, and let's fuse into it, inline in, which would be the method for bar. Don't even have a function call, put the code straight inside there, and then put the other block at the end. Linearly gone through it, no jumping around, very fast. Choosing when we do this sort of thing. But we've got to be aware. We have a very small instruction cache on our CPU. We have only 32K in our L1 instruction cache. We've got to use that wisely. We don't want to inline everything. We want to inline the things that are worthwhile. We don't know that unless we measure, so we have to be feeding the data into measured. Our runtimes can do this sort of thing. Cliff Click, who wrote a C2 compiler for Java, I've had many great discussions with him. That's one of my favorite quotes from him. Like, inlining is the optimization. Because once you inline code, you don't just save the function call overhead. You can see a much larger space of code and apply other loops, like removing duplicate work. Like, you've done that, and you've done it again. I'll just do that once and save the value. We can unroll loops. We can merge loops together. We can allied locks. There's lots of really interesting things we can do once we start to inline. But it's knowing where should we be inlining, so how do we spend that budget well. There's loads of statistics about where our time is spent in code, and a lot of it suggests loops are where we spend probably 80% plus of time in our code, but which loops? Which loops do we need to optimize? Which loops do we not care about? If this loop is executed a lot, one of the things we can do quite well is unroll it. So rather than check and iterate and jumping around so much, we'll unroll it and maybe do 4 iterations of it per iteration of the loop. That becomes a good optimization, but it creates more code. It will use up more of your iCache. Where's the balance? So drawing that balance up, and again, some of our runtimes have got good optimizations for choosing when we do this, when we don't do this. And we can start doing other interesting things, like some of those methods that we're using this evening that's hot. If we know what CPU we're running on at runtime, and I don't mean here, am I on x86 or am I on ARM? It's which version of x86 or which version of ARM may have different instructions. than some of the others. So for example, if I want to count the number of bits inside an integer, that's quite a few instructions to do that. But there's a pop count instruction that comes with SSE 4.2. And if I know my CPU supports SSE 4.2, I can just call a single instruction without even a function call. The runtime can just decide to do that. Now, static compilers can do that as well, but then you're compiling for a specific architecture. So you want to take advantage of the latest features, you have to compile for that. Your code won't run on an older version. You would end up having to manage multiple versions of it. So it's kind of interesting balances to what we end up dealing with. Polymorphism is probably the most interesting thing that managed runtimes can deal with that static compilers really struggle with. So I have a shape. It's got a polymorphic method, draw. I'm going to call that method now. How many types of shapes do I have? Let's say I only have one type of shape. I don't want to do a virtual dispatch. I don't want to go through a jump table. I'm just going to call the method directly, or even better, inline it to that call site and just use it directly. Say I have two versions of that. Well, I can just do it with an if statement. I don't need a jump table. If I've got more, there's some other options I can go through. So typically within, say, the JVM, once you reach 3 versions of something, it will go polymorphic. At sort of 1 version and 2 versions, it's got some optimizations. If you go to something like V8 with JavaScript, it stays with tests up until 4 versions and then goes polymorphic beyond that. So different interesting implementations to how it's dealt with. We can also even add a nice little feature called inline caching, which comes right back from the Smalltalk days, where of the types of shapes, say 90% of them are polygons, and there's a few squares and a few circles in there as well. Well, for the polygon one, I can cache the code for that one and do the jump table for the others and get the benefits based upon runtime data. It's really nice and it's neat. But also, it's also call site related. It's not for all the places you use shapes. You can make these optimizations per individual call site. So a different method in another place may have a different profile, and you can make different optimization decisions. Nice things that are done via runtime. And we do this through things called class hierarchy analysis. So when we load a class, if we haven't loaded another version of that class, we know that call site is good to be monomorphic. The class loader loads another version. Okay, I made a mistake optimizing for just one case. I happen to have 2. I can revoke that. I can produce a version for 2 and go forward. I load a 3rd one. I can change my mind again. It's agile. It thinks about what's going on. It can deal with this sort of thing. I've seen this sort of performance pay out. It's the thing I miss most when I'm writing C++. When I've been using Java for a while, I end up really missing some of these optimizations, and they make a big difference. It also shows up a lot in C# versus Java. C# doesn't do this sort of stuff as well as Java does it. So kind of quickly in summary on that section, we can have optimizations based upon runtime data. And they can also have bets taken that you can be wrong on. You can revoke the bet. You can do it differently again later. So let's get round to the garbage collection. So that was just giving you a flavor of some of those things. There's many, many things our runtimes can do to optimize the code, but you start to get a picture of with runtime data, you've got a lot of choices available to you. Garbage collection. It's really one of these terribly named things. We don't collect garbage, we harvest applications. And like our whole industry is terrible for naming things really badly. Like, one of my favorite misnomers is random access memory. We don't want random access, we want arbitrary access. So when I go access memory, just give me random data. No, I want exactly what I've asked for. So we gotta be careful with how we name things. But garbage collection, the real key to this is actually not the cost of allocation, it's the cost of reclamation. And the longer something lives, the greater the cost. So to steal a quote from Billy Joel, only the good die young. So if you're designing your applications, you want your objects to perform really well, keep them around for the shortest possible time. It'll really help the garbage collector. But let's see what all it can do for us. So based upon this idea that sort of most objects die young, it's called the weak generational hypothesis. We end up using generational garbage collectors. So classic sort of picture of how the JVM lays out its memory. We have a young generation, which is made up of Eden and survivor spaces, and we have an old generation where objects are tenured. Now let's go into each of these sections and look what happens. But before we do that, let's have a quick look at how a modern server is set up. We tend to have multiple CPU sockets, and inside the CPU sockets, we've got multiple CPU cores. We have a really interesting distributed system in a box. Now, you think distributed systems are only something that happens across servers? Everything is distributed these days. It's just fractal, and it all happens at different levels of scale. All the patterns just keep repeating themselves. So within the socket, we have multiple cores. They each have private memory in their L1 caches. They share that with L2, and then they have buses that connect across the different machines. So you want to have that locality of reference working for you. So you need to design your memory subsystem to respect the locality of reference of what's going on there. So that's a 2-socket server, the typical pizza boxes that you're going to get. And if you've got up to about 10 cores in each socket, they're relatively simple. If you've got more than 10 cores in a socket, it gets complicated, and it's surprising again. And this is where I mean about the fractal stuff. So this is a picture of one of the latest Broadwell Xeon chips, a single chip. This is not a server with multiple chips. A single chip having 24 cores in it is actually separated into 2 segments with 2 independent rings with networking between them. There's a switch in there. This is not a rack. This is inside silicon in the single machine. And where we end up locating stuff starts to really matter. If our cores, which are around the outside, and then in the inside we've got our cache segments, we want these to be as close together because it gives us better performance. Now, taking this, let's go back to our picture of what the garbage collectors do. So in the young generation, the reason why our allocation is very cheap is we allocate from what are known as TLABs, thread local allocation buffers, and you get 1 per thread. And you allocate out of that if there's sufficient space inside them. So all your small objects that get allocated out of there, it's incredibly cheap. It doesn't share with other threads. It's a very simple increment of a pointer for where the next object needs to be allocated. And they're all nice and close together. So we get this nice locality of reference. We can be NUMA aware on these complicated servers that we have now. And we can avoid things like false sharing on those cache lines that I mentioned that are 64 bytes at a time. So this all works very nicely. One point on this, where this can go horribly wrong, is if you like to run with very large numbers of threads, you're working against this because you're going to have a buffer per thread. And you can end up in a case of where you've got a buffer per thread, they're all just very partially used, and you've got one little greedy thread, and that one little greedy thread needs to have more of them. There's not enough space left. It has to cause a full GC cycle of the young generation to go and deal with that. So kind of be aware, everything's got consequences. Whenever we have a collection of the young generation, what happens is we copy the objects that are retained into the survivor spaces, so put them all close together again. Get the locality of reference. We copy them between the survivor spaces a number of times until they've reached a certain age. And then beyond that, we need to move them to the old generation. So even at this level, we can be kind of NUMA aware. We can have lots of nice parallel algorithms, lots of things that can work in our favor within our garbage collectors. And then, if things live for a longer period of time, they get copied to the tenured generation and they get dealt with in a different way. So notice that there's more things you have to do with an object the longer it stays around. This is why the good die young. We want to keep things around for the shortest possible time. But when they go into the old generation, we can start doing other interesting things. Like as part of moving them in through there, we can do stuff concurrently, like we can do some concurrent compaction with some types of collectors, but we can also deduplicate strings with some of our collectors. So many applications have same value of strings used multiple times, using up a lot of your memory. Let's compress them down and deduplicate them. These sort of things are possible. So let's look at what happens when we actually do a collection. So we've got a region of memory here. The bits that you see there is what's retained. So this whole space was used, but the majority of objects have died. They don't need to be capped. We need to retain. And let's say this was something like an array list. We've got a list. That's the big long bar in the middle, and then it's got lots of other little objects that it references. They're all over the place. Accessing those will be relatively slow. How do we make it faster? How do we make it better? Well, when we do a garbage collection, what happens is it does a depth first copy. So it copies all of the children of that, moves them over, puts them all together, and makes them nice to stream through if we need to iterate through them. Then it will copy the array itself. All nice and compact. It's the sort of thing that garbage collectors are doing when they go through the cycles. We can get benefits from them as they're running. So they've got costs, they've also got benefits. And think about what this does to our operating system pages, our cache lines. It keeps it all nice together, makes it work nice and friendly with our caches. We move forward to things like G1, lots of other interesting collectors coming out. We start looking at, can we compact concurrently? Most of our compaction of our algorithms all happens by stop the world, which is the thing that really annoys us in low latency applications. Can we do this concurrently? Well, things like G1 deal with this by dividing up the whole heap into regions, and it collects the regions with the most amount of garbage. That's why it's called G1. So that's going to be the least amount of copying, and basically breaks the problem down into bite-sized chunks. But it's still not perfect. It's a step forward in some ways, but it's got quite a lot of overhead. If you want to look at some really nice collectors for this, the Zool C4, the concurrently compacting collector, can do this totally in the background without pausing your application at all. So you can actually have a low latency financial application that doesn't experience GC pauses any more than the operating system would have put on you anyway. And it runs very fast. It works very well for large heap applications. So there are great collectors in this space and others appearing all the time. Like Shenandoah is now actively going forward in this space. So where's next for GC? So there has been other interesting things happening. Well, if you've got objects that have got interesting properties or elsewhere, so let's say there's a person object that represents me, and I have a date of birth, and maybe I've got a favorite color, and maybe I've got a few other things about me. If those are all objects elsewhere on the heap, those are data-dependent loads to go get them. What if we can just inline all of those objects into the aggregate object and keep it together? So have concepts that stay together. Now, in something like C, it's very easy to do with structures inside structures. We can control over other. We could make additions to the language that will make this possible. So things like C# actually let you have a fair amount of control in this space. So it's a kind of nice compromise. Java is kind of weak in this area. But never mind even changing the language. There's a lot of research that shows that this can benefit if it's done automatically. So if you have an object and it's got a field that's final, and that field isn't used anywhere outside of the object, why not just get the garbage collector to join them together as a single object? Logically, it looks the same to you, but underneath, it's all kept together, can be made much more performant, and can be really very surprising, the results that's coming out of that. So we're starting to see some nice advances in this area, but again, based upon runtime information, doing the right thing with our applications. So if we compare garbage collection with manual memory management, what sort of things do we need to consider? Well, things that we've got to worry about on the managed side is like the GC implementation itself makes a huge difference. Like how good a quality is your GC algorithm? And there's a wild difference across many languages and many VMs to how good they are. There are some great ones, there's some that aren't so great. They all have some interesting things to deal with in the background. Like we have to do this thing called card marking. So every time you set a reference on an object, we need to mark a card table to say which part of the heap has changed to help the garbage collector. That takes a fair amount of memory and also takes time to scan. We have read and write barriers to update our objects for when we read fields, when we write them, and some of them have more cost than others. So if you run something like parallel old, it's very cheap for that. You run CMS, it gets a bit more expensive. You run G1, it gets a lot more expensive. And we start to see the impact in our throughput on some of that. So garbage collectors, they do have a memory overhead. Usually the more memory you allow them, the better they perform. So you need to have that memory. You need to have additional CPU resource to let it run. So even if you've got a concurrent one, that's great, but you need to have the cores for it to run on to get the benefits from it. What about the native side? Well, again, there's a massive difference in which malloc implementation you have. Some are much faster than others. Some have got nicer implementations. They have things like arenas and pools underneath them. They can have contention. You can have serious contention problems allocating a lot of objects in C or C++ or other languages, and you can get wastage inside some of those. You can also get fragmentation, where you've got a lot of space available, but you can't use it because it's smaller chunks than you need for a single allocation. We have some interesting problems there. And debugging, if you deal with a lot of C applications or whatever, you spend time chasing down pointer dereferences that are wrong. And we have to deal with them and the debugging. But the real elephant in the room with the native applications is their allocators can be relatively fast until you pass something across threads. As soon as you pass a reference across threads, you have some serious issues with the collection later on with that. That's where the real costs come to hide. And when everybody talks about allocation being cheap or allocation being free, allocation is not the thing you worry about, it's reclamation. It's always the reclaiming is where the costs come to be paid. And we have to do that later on. And all types of allocators suffer that in some way. So that's the GC, that's the instructions. Where do algorithms come into this? This is the kind of really interesting part. And kind of what is the most important thing to performance? Like, in the room here, what do people think is the most important thing for making a high-performance application? Latency? The algorithm? Partially. I would argue the most important thing is your own time. Having the time to come up with good algorithms, make good choices, do the right sort of thing, and time is something is very precious in most of our projects. Like, who ever complains of having too much time to complete a project? It just doesn't happen very often. I love this quote, like, if I had more time, I'd have written a shorter letter. I think it so applies to our code as well. You can make code much more elegant and across all dimensions, like its reliability, its robustness, its clarity, its usability, its performance, if we have time to do it and do it well. So if you're going to make something faster, you'll do a lot of these sorts of things. Like, you'll avoid duplicate work. So you may have one language which is a few percentage points faster than another language, but if you do the same amount of work twice because you haven't realized that you've actually done the work twice in your code, it doesn't matter which languages you've chosen. So we end up dealing with lots of these different things, but like what algorithms we choose with data structures, and really what APIs we design, which is a huge subject in its own right, we can make a lot of this better. So when you're dealing with a large project, it's really difficult to do everything well. That's the really interesting challenge. You can have micro benchmarks, you can have all sorts of interesting things to deal with, but on a large project, how do we manage it? How do we do everything well? So we want to end up doing the right sort of things around this. And to performance test and do stuff well in code, we've got some of these unusual skills for people. Like, we've got a profile. We've got to have telemetry. We've got to have performance models of our code. And that takes time to develop and do well. So there's an interesting story of a project I've worked on. So I work on a messaging system called Aeron in part of my time. And we developed the first version of it in Java. It competes with native implementations of very fast messaging systems. The nice thing is, it's actually faster than any of them. And the key to why it's faster is algorithms. We were able to develop algorithms that are just faster than the algorithms that are existing in some of the native implementations because of a lot of the history and learning and things that we brought to it. And the really important point for me was the kind of time to performance. So from starting a project to having something that performed well. I'm very comfortable with C, C++, many other languages, even a bit of assembler. And I like doing these sorts of things in managed languages because I get to an answer quite quickly and I can refine a design. Now, you can choose to later port to another language, and we have done this. So Aeron was first developed in Java. We got to the point where it was much faster than the existing implementations of other messaging products out there, and then we ported it to C++. And it's been ported to Go and to C#, and it's kind of interesting. What do people think would be the fastest? What would be the fastest implementation when you've taken kind of the same algorithms and you've moved them to the different languages? Who would think Java? Few hands? C++? C#? Go? It kind of mixed, and a lot of people haven't put their hands up. Well, when we just did them first time and compared them all, Java was the fastest. After some refinement, the surprise for us was C#. C# actually ended up being the fastest implementation, but it took a fair bit of time. C++ is very close and can potentially be the fastest of them all, but it takes a lot more time and refinement to get to that point. So the time to performance is kind of interesting. So how much effort you're going to put in for what performance you end up getting at the end of the day. And it ended up like the reason why we struggle with Java getting any faster is it doesn't have enough control of memory layout. We struggled with C# and C++ because of the virtual method dispatch and some of the other cases. So once we got around some of the virtual method dispatch and some of the memory model issues, C# was really good. And it surprised me that it was actually a nice language to make stuff go relatively fast, but having enough control. So there's a kind of interesting lesson for the Java architects, and that is allowing a bit more control to the developers means you can do some really interesting things. You probably don't want to go as far as C++, where you can make it even faster, but the effort is much, much higher to get it right. And there's a lot of other examples of this out there. So C# itself used to be written in C++. And then they decided to dog food. And when they produced the Roslyn compiler, they wrote the compiler in C#. It was a bit of a painful time to begin with, but in the end, it improved the language and made things really interesting. They were able to take advantage of other algorithms they couldn't in C++, and now they've got a compiler that's faster. So interesting where some of this stuff is going. So you start asking, well, where do you spend your time? Do you spend your time sort of debugging the pointers, dealing with that, or do you spend the time understanding hardware? Do you spend the time looking at new algorithms, researching ways of doing stuff, refining things, doing that thing of having more time and writing a shorter letter? I find that that pays off much more than being so precise in a particular language, especially when you want to evolve and iterate stuff. When you come up with a good algorithm, porting to other languages is relatively easy, but that experimental side, I find it actually works better in managed languages. And it's why I particularly like dealing with something like Java in finance. Then we've got GC. The thing that really stands out with GC is the fact that we can now do things in concurrent programming that you just cannot do in native languages. There's some algorithms that are just so difficult to track that it's much, much easier if we've got a GC, and that's another interesting talk in its own right. So kind of quickly in closing here, and kind of what's the future hold in this space and what's kind of coming? Like, anybody remember the arguments about assembler versus compiled languages? I have lots of friends who worked in the games industry, and I remember them going through the whole pain of compilers were coming in, and the argument was a compiler can never be faster than hand-coded assembler. And then things got so complicated that no one could keep it all in their head, where one method that could make it maybe faster than the compiler, but not something bigger than that. In the future, with some of our applications, we could be there. But there's some things to think about. Like, what about the footprint? Like, managed runtimes require more memory. You can't get away from that. They take longer to start up and warm up, but there's alternatives out there. We're starting to get ahead-of-time compilation, even like coming out in Java 9. Things like Azul Zing can store its profiling information and reuse it again in the future. So these things are even changing. This is interesting. Anybody been to Brisbane in Australia? There's a research project going on down there. This is a huge, big interactive wall. The graphics is being rendered here in real time. You can interact, you can stroke the water, you can deal with this in really interesting ways. So this is very complex, real time, very strong interaction. What do you think that's written in as a language? JavaScript? It's a language called Impromptu, which is a version of Scheme. So back like Lisp almost. But it's got a real-time garbage collector, and it's got some really nice intrinsics for doing the graphics you can call into that. And now they're doing really cool stuff. This was done to do music and graphics and other stuff that's really very complex. Like, that's a lot more complex than most web pages you get to see, let's face it. And it can work really well. So kind of think about, if we have infinite time, we've got lots of choices, but we don't have infinite time. And where do you spend your time? And sort of think where the payoffs happen to be. It's an interesting thing to ponder. On that, I'll thank you very much, and I might have time for a couple of questions.
Any questions?
Thanks for this awesome talk. You were briefly mentioning when you were going through the overhead of garbage collectors that different ones like the parallel one, concurrent mark, and sweep G1 and so on, they have slightly different efforts that they put into their, what do you call it, card marking or so, and also when they would have to inject memory barriers and so on. Can you give a few more details there?
Yeah, sure. So card marking is one part of it. So whenever you've got an object, so let's say, for example, you had an object and you want to set a field in that object. If it's a reference, so references are treated different from primitives. So I've got a person object, and I want to set a date. And say I want to set the date is my birth date, and it's wrong. So someone's going to correct it and reset the date. So they're going to store a date object. Whenever you set that field, the garbage collector has to be aware that it needs to walk from that reference to the object to know it's been retained. So if the person object that's in the old generation maybe at this stage, it's going to be now pointing to a new date that's been created. So when a garbage collection cycle occurs, it needs to know how to find that object and keep it and retain it. And the way it does that is through a store barrier, and that store barrier has various amounts of logic depending on which type of garbage collector it is. So they all will typically have a minimum of a card mark. So what a card mark is saying is that there's an object somewhere in the heap that's pointing to an object here that's going to be retained. So I need to know what has changed in the whole heap, so I don't need to scan the whole heap. And the card mark, so like a typical card will be, they'll use a byte to represent 512 bytes region of memory. So if something changes in that 512 bytes, it updates that card to say it's been done. And that's like the simplest case. Some of the other garbage collectors, depending on their complexity, will do more. So things like G1 has got much more complicated data structures than just the cards to track the regions. It needs to know what the inter-region references are, and it'll sort of make those coarser or finer depending on how many references. So one of the things you can do that really hurts the performance of G1 is have lots of interrelated object references that are across different regions. If you have less references, that becomes cheaper because it can more precisely mark things. As you get more references, it goes coarser because it tries to keep the amount of memory down, but then changes the data structures to deal with that. And just all garbage collectors have got different structures that they update to deal with that. And so it depends on which one that store barrier cost can increase. Does that help?
Do we have time for one more?
You have surprised me talking about inlining code because I really hate duplicate code. So if it's really more efficient to have the code inlined, can the compiler do it for you when it compiles the binary?
Yeah, so the question you're saying, you don't like the duplicate code. Well, this is at a compiler level, not yourself. So you're not copying the code in, the compiler is choosing. So say in C++, you can use the inline keyword. So you're not copying the code, you're just saying this function will be inlined to this point and stuff. But it's kind of interesting. Although the duplicate code question, as a separate issue, I would challenge anyway, because I think dry can be really bad to our designs as well. Yes, we don't want to have duplicate code, but duplicate code across projects means you're decoupled. Getting coupling across modules where you say, I'm going to dry out everything and put it elsewhere, it's a kind of interesting subject in its own right. But yeah, but you don't need to worry about it. It's something the compiler and the runtime does for you. Yeah.
I'm afraid we're going to have to stop there, but I'm sure Martin will be
Sure.
pleased. anyone wants to accost him on the way out. So thank you very much.
Thank you, everyone.